Hi everybody, this is the second part of the voltage lesson for the electricity topic for Physics A-Level. In this video we're going to look at some exam questions on voltage and PD and energy. So we're going to review the key ideas from the previous lesson, and as we said, exam questions A star, we're going to try to find those. It's quite difficult because we've only introduced two topics thus far, current and voltage. So a lot of the high grade exam questions will be synoptic. That means they'll draw in lots of ideas from across the topic. So yeah, they're the hardest ones I can find based on what we've covered so far. So have a quick look at these 5 questions. Just remind yourself of these key ideas. Once you've done that, then you can press play on the video and just check that you've got these key ideas correct. So as we saw in the previous video, voltage is the energy per unit charge. V equals E over Q, or W over Q. So 1 volt follows from that. 1 volt is 1 unit of energy, which is 1 joule, divided by 1 unit of charge, which is 1 coulomb, so 1 joule per coulomb. We talked about the difference between potential energy, PD, and electromotive force, EMF. They're both basically the same thing. They're both voltage, effectively, energy per unit charge, but PD is associated with the components, where energy is converted from electrical into other forms, and EMF is associated with the cell or the battery, where energy is converted from one form, possibly chemical, into electrical energy. We mentioned voltmeters connected in parallel in contrast to an ammeter, which is connected in series, and the rules for series and parallel as shown. So series, the voltage is shared out among the components in the loop. In parallel, the voltage is the same across each component, each loop in the circuit. There we go. Right, so these are the 3 exam questions that I've picked. So what you need to do is have a read through these, pause the video, and try and answer these. Write something down, write your calculations down. Think about those exam tips that we've talked about. So show you're working out, substitute the numbers for the calculations, question 2. Try to get the correct terms. Always include the units, etc. For question 1, it says explain how the voltage varies. Now, another exam question might have said describe and explain. So we can think about command words here, but because it's a relatively straightforward idea, then the explanation will include the description. So this is probably 3 marks. So the actual relationship is this final bullet point: the voltage is proportional to length. So how do we get to that? So the first one, resistance is proportional to length. Now, we will look at this in more detail when we look at resistivity, and we can show this algebraically, but we haven't covered that just yet. Hopefully that is fairly intuitive. So if I have a piece of wire and it has a resistance of 10 ohms, if I double the length of the wire, then the resistance will double. It's a proportional relationship. And the reason why, as we'll see later on in the topic, is that there are more collisions. It's more difficult for an electron to travel through double the length than just a single length. So we have this proportional relationship. The second point is that voltage is proportional to resistance. Now, we haven't looked at V equals I times R. You're probably very familiar with that from GCSE. So if the current is fixed, then V is proportional to I. So if I double the resistance, I double the voltage. This is a really key idea throughout this topic, the idea that a larger resistance component needs a larger voltage to push the same current through, and it's a proportional relationship. So these 2 ideas you may have come across before, and we will look at these in more detail later on in the topic. So mathematically, if these 2 are correct, then it follows logically that voltage must be proportional to length. So what we're saying is, for example, if I have a battery, a 6-volt battery, and I have a resistor, if I measure the voltage at a particular point, let's say it's 0 at this point, then as I move along the resistor and measure the potential difference between the right-hand side and any particular point on the resistor, then the voltage will increase until it reaches a maximum of 6 volts. So ignoring the resistance of the wires, which we normally do, then the potential difference across the resistor is 6 volts, and it will vary between 0 and 6 in proportion to the length. Okay, question 2. Here we go. So this is a fairly typical A-level question. It says 4 marks. It could be 3 or 4 marks, depending on the exam board. So we're applying what we did last lesson, this relatively straightforward formula from GCSE of V equals E over Q. And if you're not quite sure how to do it, it says the gain of kinetic energy. Okay, we haven't talked about kinetic energy thus far. But in an electron tube, it's a partial or a complete vacuum. We assume it's a complete vacuum. So there's no energy lost. So if I'm looking at 1 electron, well, I know the elementary charge is 1.6 10 to the minus 19. And I know the voltage we're given that's 1800. So I can work out the energy transferred to the electron. So E equals V times Q, or W equals V times Q. All I'm doing is multiplying these two together to get this tiny value of energy in joules. And we're assuming that if the electron has 0 kinetic energy to start with, because it's just at rest, as it's accelerated to the positive electrode, it gains lots of kinetic energy. And this is what we're calculating. So this is why the idea of voltage as the energy transferred is really important. Energy is transferred to the electron, therefore it appears as kinetic energy. So mathematically, relatively straightforward, but conceptually, understanding that this is now the kinetic energy of an individual electron is really, really key. Okay, so then all we need to do is to get our expression from GCSE. Kinetic energy is half mv squared. Rearrange this to make V the subject. So it's going to be the square root of 2ke over m, or if you prefer, the square root of ke over half m, which is exactly the same thing. So 2 times our previous value divided by the mass of an electron, which we are given in the question. In the exam, this would be in the formula booklet, the data booklet, you have to find that. And we get a value of 2.5 times 10 to the 7 meters per second. That sounds about right, because electrons move really quickly. It's very rare to have an electron which is moving through space at 20 meters per second or 500 meters per second. So if we're looking at 1 electron accelerated through a large voltage, they're really, really shifting, approaching the speed of light. So that seems about correct. As always, show all your working out. So even if you couldn't get the right answer, if you made a mathematical mistake, if you wrote down half mv squared and rearranged it and tried to put some values in, you might get 1, possibly more marks for your answer. Question 3 says use the laws of conservation of energy and charge. So we've mentioned both of these in the previous lessons. Derive the rules. So the word derive is something which most exam boards expect you to do. This is show algebraically why these rules are true. So we know what the rules are. So we could just write them down. We might get a mark possibly for that, but probably not. The 6 marks question mark, well, it could be 4 to 6. Some exam boards expect you to be able to do this. If this is part of the specification, it probably wouldn't be 6 marks. Some exam boards, this is seen as extension, so this could be 5 or 6 marks. So this could be an A-star question, potentially. But if you haven't considered this before, then you probably would find this very difficult. So let's have a look at the first one. So a series circuit. Okay, so let's imagine we have a battery or a cell which provides a total energy ET. And we have 3 resistors. Each one takes some energy from the total, E1, E2, and E3. So our first starting point, based on conservation of energy, is what does the total energy ET represent? And hopefully you can see that that would just be the sum of each of these energies, E1 plus E2 plus E3. If you think about it, that should make sense. If I have 100 joules of energy here, then that's going to be shared out among these 3 resistors. If they all have the same resistance value, it will be an equal share. If we have a larger resistance, then it will have a different value of energy. Okay, that's our starting point based on conservation of energy. Then we need to do a substitution. So using our formula, V equals E over Q, we make E the subject, E equals V times Q. We're just going to substitute VQ for each of these values here. So VQ total, that's the battery, is equal to V times Q for resistor 1, plus VQ for resistor 2, plus VQ for resistor 3. Right, so how do we simplify this? So think about Kirchhoff's first law. we talked about the current being the same all the way around the circuit. We also mentioned conservation of charge. So Kirchhoff's first law is based on conservation of charge. The charge at any particular point must be the same. The rate of flow of charge, that is the current, is the same. In other words, the total charge coming from the battery must be equal to the charge in the first resistor, which is equal to the charge in the second resistor, which is equal to the charge in the third resistor. In other words, what we're saying is that the Q is the same all the way through. It's not different. So QT is equal to Q1, which is equal to Q2, which is equal to Q3. So all we need to do is cancel out the Q's, get rid of those, and we end up with VT is equal to V1 plus V2 plus V3, which, as we know, is the rule for voltage in a series circuit. So we've shown algebraically, derived, where this expression comes from. Okay, same idea for voltage in parallel circuits. So our starting point here is not conservation of energy, our starting point is conservation of charge. So if I have a parallel circuit, as shown, my total charge here, QT, coming from the battery, some of it goes along the top loop, Q1, some of it goes along the middle loop, Q2, and some goes along the bottom loop, Q3. So in this case, as we know, parallel circuit is not the same as a series circuit. So we need to think, well, what is the relationship mathematically between these terms here? Well, hopefully you can see that the total charge, QT, is equal to Q1 plus Q2 plus Q3. We said in the first lesson that the current, the charge, splits and then reforms. So that's our starting point. Part 2 of the derivation is we're going to go back to our expression here, V equals E over Q, but now we want to make Q the subject. So Q is equal to E or W over V, so I can write this expression again, but rather than Q, I write E over V. So E over V total is equal to E over V for the first loop, or the first resistor, plus E over V for the second resistor, plus E over V for the third resistor. Right, so now we're going to use conservation of energy. So if you think about the series, we started off with conservation of energy and then applied conservation of charge. For parallel circuits, we start off with conservation of charge and then apply the law of conservation of energy. So once again, as we said up here, the total energy is equal to the energy, or the sum of the energy in each of the resistors. And that's absolutely true here. That must be the case. If it wasn't, then we'd be getting energy for free and we'd be violating the law of conservation of energy. So the total energy must be equal to E1 plus E2 plus E3. So if I look at the top of each of these fractions, I've got E total, E1, E2, E3. That expression can only make sense if we're dividing every term in the expression by the same value. So if Vt was not the same as V1, or not the same as V2, which is not the same as V3, then that would no longer be true. So this is a little bit more difficult. I think it's easier, if we go back to this one here, to divide through by Q. I think we're used to doing that, but this is a little bit more tricky, conceptually, to get our heads around. But it must be true. So in order that energy is conserved, then this value here, let's say the total voltage is 10, divide by 10, divide by 10, divide by 10, divide by 10. The value of the voltage must be the same for each of these terms, otherwise energy would not be conserved. Right, so as I said, this is the best we can get for a grade A star question this far into the topic. As we get further into the topic, we'll be able to draw on lots of different ideas and look at more complex questions, which are definitely A star.